Let's jump right into this explainer. If you've been working with large language models, you know that building a basic AI wrapper is pretty easy, right? But making that AI actually remember things across days, weeks, or even months, that is a whole different ballgame. Today, we're going to unpack the exact architecture you need to move beyond those basic wrappers and develop robust, scalable memory systems with true long-term semantic understanding.
This right here is the fundamental challenge we face as developers. Look, we've all been there. When an AI tries to remember everything without any kind of strict management, it inevitably leads to a massive token overflow. You basically end up with a system that either completely forgets what you said 5 minutes ago, or it just outright crashes because the context window is maxed out. I mean, who hasn't seen that dreaded context limit exceeded error?
Before we write any actual code, it really helps to map these technical concepts to human cognition. Think of your active thoughts, what you're holding in your head at this very second, as the conversation buffer. But your entire life's knowledge, that's your vector memory. It's stored deep down, and when you retrieve it, you do it based on meaning and association. You're not doing a literal keyword search of your brain, and your AI shouldn't either.
Okay, here's our roadmap for this explainer. We'll quickly cover the semantic memory revolution, translating text to vectors, integrating a vector database, token trimming, building our hybrid system, and finally, best practices for scaling safely.
Section 1. The Semantic Memory Revolution.
Honestly, practically every developer has written a naive memory class exactly like this on day one. You initialize short and long memory arrays, and then you just append every single message to a list. But returning that full, unfiltered array to the LLM causes an immediate token explosion. It makes your inference incredibly slow and feeds the model a highly noisy context that just ends up confusing it.
Section 2. Translating text to vectors. Let's see how we fix that.
This brilliantly illustrates why exact keyword matching fails so miserably. If a user asks, "How do I trade breakouts?" a traditional keyword search is going to find absolutely zero matches for momentum strategy. But embedding models, they convert raw text into dense mathematical vectors. They capture the actual semantic meaning. Because momentum and breakouts are conceptually related in the financial world, their vectors are mathematically close together, easily bridging the gap between those two completely different phrases.
Section 3. Integrating a vector database. Getting this into your code really comes down to 3 practical steps. First, you encode your text strings, something like user trades nifty options, into mathematical arrays using a tool like sentence transformer. Second, you instantly index them using a lightweight local vector database like ChromaDB or Face. Third, when a new query comes in, you run a similarity search algorithm to compare the new vector to your database, instantly pulling the most semantically relevant memories to feed to your LLM.
Section 4. Token trimming and memory management. Now, even with the smartest vector databases pulling relevant facts, LLMs still have strict, hard context limits, usually anywhere from 4K to 128K tokens. This is why a basic sliding window, like just keeping the last 5 messages, simply isn't enough. 5 messages could be 50 tokens or 5,000 tokens. Advanced token-based systems are actually aware of the token count. That gives you excellent scalability and basically zero risk of overflow, which prevents degraded answers and truncated context.
Look at how elegant this solution is. By proactively utilizing a simple while token count is greater than limit loop, you're doing aggressive token trimming right in your code. You just drop the oldest tokens until you're under the limit. Implementing this one simple check guarantees better context quality, drastically lowers your inference costs, and highly improves attention allocation because the LLM isn't distracted by overflowing text.
But here is the thing. Token trimming only handles the short term. Knowledge compression is absolutely essential for true long-term system scalability. You simply cannot store infinite conversation logs. You must shrink massive message histories down into dense semantic facts. Condensing 500 chatty messages down to a single fact like user prefers breakout trading saves a ton of tokens and massively boosts your retrieval accuracy.
Section 5. Building hybrid retrieval systems.
This is where the magic happens. A true hybrid retrieval architecture merges all these elements seamlessly. It means a single user query can pull the active recent context from your buffer, persistent facts from a traditional database, semantic similarities from your vector index, and specific IDs using exact keyword matches. All of this happens simultaneously to construct the absolute perfect prompt.
When you're writing your hierarchical memory design code, building progressively is key. You start with level 1 as your active buffer, level 2 for session summaries, level 3 for your long-term SQL database, and level 4 for deep vector semantic memory. Structuring your retrieval function to pull from L1 down through L4 guarantees maximum intelligence without ever overloading the model's context window. Section 6. Scaling safely with best practices. Let's run through a rapid-fire rundown of what to do and, more importantly, what to avoid.
When tuning your vector search, the math matters. You can vastly improve your accuracy by matching the right similarity technique to your specific needs. Cosine similarity is pretty much your go-to for checking semantic closeness regardless of text length. But understanding how that differs from Euclidean distance or dot product is crucial for a highly accurate retrieval pipeline.
Now, for the love of coding, please make sure you avoid these common mistakes. Ignoring context limits or failing to apply retrieval rankings will absolutely cripple your system's performance. And a huge one I see all the time, storing embeddings without metadata. If you just store a vector without tagging it with a date or a user ID, filtering your semantic searches later on becomes virtually impossible.
Conversely, implement these best practices and your memory pipeline will scale beautifully. Apply that aggressive token trimming we discussed. Keep your short-term memory strictly separated from your vector memory, and here's a massive pro tip. Cache your frequent retrievals. If users keep asking the same semantic questions, caching those vector match results will absolutely crush your latency times.
Ultimately, integrating embeddings and hybrid retrieval gives your AI genuine contextual awareness. As the quote says, vector memory transforms AI from keyword matching systems into meaning-aware intelligent systems. It stops acting like a fancy word finder and actually starts comprehending the deeper intent behind what the user is asking.
And that brings us to the most exciting part. You now have the coding blueprint to effectively cure AI amnesia. You're no longer limited by narrow token windows or keyword exactness. The infrastructure is there. So if your system can endlessly remember and retrieve information based purely on its deeper meaning, what complex real-world problems are you going to teach it to solve next?